So our last presentation is by Xueyam. Our title is Deep Learning Can Help Radiologists Segment the Pulmonary Embolism Using CT Angiography.
Thank you for giving me this opportunity to present. So my topic is using deep learning that can help radiologists segment pulmonary embolism using CT angiography. So, as a brief introduction, so pulmonary embolism is caused by a blockage in pulmonary arteries, and it can be diagnosed with CT angiography scans. So the location and size of the PE are important clinical variables for doctors to plan for such treatments for patients. But the segmentation of the ground truth of PE from a series of high-resolution studies are very time-consuming. So we hope deep learning could facilitate doctors to detect, differentiate, or localize such diseases, and thus increasing their efficiency and improving the diagnosis. So we collected 110 patients with 235 studies with over 23,000 slices, and we split a data set into the training set, the validation set, and both of the sets are comprised of the original image and ground truth mask. And the validation set is used to optimize and tune the parameters in the training set. And we're gonna generate the predictions from the slices on the test set and compare the prediction with the ground truth mask. So the ground truth was annotated by Siemens single via through the region growing algorithm by a board-certified radiologist. So we proposed the UNet deep learning model to help us generate the output segmentation. So through this architecture, we could have our segmentation. So this part is called the downsampling process, which is also known as the encoder process. So this is used to encode the information and to have the algorithm to learn what kind of information is included in the image. And this part is the upsampling process, and it is used for the UNet to learn where the information is. So by concatenating where and what the information at the same level, we can have our output segmentation. So to evaluate the performance of the model, we introduced the following terms in computer vision. So we use DICE score, which is also known as the F1 score, and intersection over union to evaluate our model. These terms are used to evaluate the similarity between two objects. And we also used true positives, false positives, and false negatives to evaluate our model. All of the terms are all based on the overlap between the predicted segmentation and the ground truth. So the DICE score equals to 2 times the overlap over the sum of overlap and union, and IOU equals to intersection over union, and these terms can be converted from each other. The definition of true positives in our study is defined as the overlap greater than 0.5, and false positives are defined as the overlap smaller or equal to 0.5, including no overlap between the ground truth and predicted segmentation. And false negatives means there's no prediction generated by the model. So we use R-square correlation and Altman plot to measure the differences between the segmentation and the ground truth. So all the x-axis and the y-axis present the area in pixel values for each mask. So we'll see the algorithm achieved 0.791 R-square correlation, which is the fair and reasonable performance. And from the blend Altman plot, we can see most of the dots are around the mean and within 2 standard deviation from the mean. And there are, of course, some outliers. The algorithm achieved like 0.48 mean DICE score and 0.455 mean IOU. There are 376 slices were considered as false positives by the algorithm, and 569 slices were considered as false negatives, which there's no prediction generated. And in terms of successful predictions, there are 2339 slices with the threshold greater than 0.5. So here is a very successful, like a toy example of an image. So this is the original image, and this is the ground truth generated in single via, and this is the predicted mask. And we overlay the predicted mask on the ground truth, which comes with this image. So it's almost the perfect example. Here are some examples of failure images. So it's the first false positives where there's no overlap between the ground truth mask and the predicted segmentation. So it's really hard to see. So let's zoom in a little bit. So we can see the ground truth is right here, and the predict segmentation is right here. There's no overlap. So it's a false positive. And this case as well, no overlap. So here are some examples of false negatives where the algorithm didn't attack any pulmonary embolism. So we do see the deep learning can help with the segmentation, but there are, of course, some limitations of this study. So we are definitely limited to the number of positive studies and negative studies. We only have 110 patients with 235 positive studies, and we didn't include any negative studies yet. And the various shapes and location and small size volume of the pulmonary embolism make this task extremely challenging compared to a segmentation task for organs. So for example, if we are going to segment like kidney, liver, or lung on CDs or whatever types of images, because most of the people will have a very similar structure of the organs, which it will make this task kind of easier. But in terms of pulmonary embolism or other pulmonary nodules, they have different types of shapes or different types of locations in the lung. So it makes this kind of segmentation task harder and challenging. So the future work will definitely include more negative and positive studies, and we probably need to propose a classification model to differentiate PE from suspect cases, because right now we've already collected we used all the positive cases that were identified by the radiologist. So if we want to eventually come up with an automatic tool, so we need this step. And of course, we need to improve our models and choose the parameters to see if we can improve from the current results. Thank you for your attention.